Hi, welcome to Lecture 20. We're going to be covering section 4.1 from the book today, um, basic notions of set theory. So we're getting ready to talk about sets. So the layout today is going to be a lot of very short sections. So there's a little more structure to it than usual, but each of these sections has just a few slides in it. Some only one. So we'll talk first about category theory, and then an introduction to sets. A couple of variants on the idea of a set. Well, a variant on the idea of a set is a multiset. And then we'll explore power sets, which are an interesting type, not a type so much as a construction one can do with a set. Finally, we'll do some computing on Sage, and then we'll kind of wrap it up. So let's get rolling. What is category theory? First off, I have to say category theory is not something that as undergrads you would typically see. It's usually, if you see it at all, it'd be in your final year, and uh, it's more common to have people study categories in grad school. The main idea of categories is that, it's been called the mathematics of mathematics. I like that idea. It's it's sort of using math to analyze math itself and seeing ways in which different branches of math can be thought of as actually representing the same thing, just the details are changed. Um, there's an excellent text, Categories for the Working Mathematician. This is probably 60 years old at this point, maybe older, but it's still worth reading. Saunders McLean, so a very good writer. So categories are not really what I'm after here. What I want us to realize is that logic and sets, the two things that, the thing we did in chapter 2 and the thing we're about to do here in chapter 4, they're almost identical. There is a categorical correspondence between the two things. So we'll take advantage of that to sort of shorten up our discussion of things in sets, because we can use the stuff we already worked out in logic. There is one wrinkle that we have to deal with in the way I'm presenting set theory. You have to work inside some predefined universal set, a universe of discourse. It's just it's potentially a shortcoming, but it will make our lives much easier to think this way. Start off with some set that we work inside of, and stick with that, and then a lot of definitions come out to work better. There was a time around the late 1800s, early 1900s, when mathematicians decided to do that with set theory. So the universe of discourse for set theory was the set of all sets. And while that sounds innocuous, around 1920, I think, a man named George Cantor came up with a real shocker that if you believed there was such a thing as the set of all sets, it produced an irreparable paradox. It broke math. You couldn't have the set of all sets and still have a consistent mathematical framework. So that was bad. And at the time, people tried to sort of bring it across to the general public what was going on by introducing a thing they called the barber paradox. You will still occasionally hear people say, "Who shaves the barber?" when they're talking about something that's paradoxical of this order. Or you may not, but it's not terribly uncommon. So we're going to be working within a universe of discourse. Now, we actually did that when we did logic too, when we had an open sentence for all x in, we always said for all x in some set, right? So what is this equivalence between logic and set theory? Let's first talk about the undefined terms, the things that we have to take as atomic. In in logic, there are these: true, false, statement, and sentence. So, we actually had something of a definition for statement, didn't we? What we didn't have a definition for was sentence. I couldn't really say what a sentence is, but if you point at a sentence, I'll go, yes, that's a sentence. A statement is just a sentence that's true. So this one's actually got a definition, but weirdly, we just can't define what true and false are. Those are. I know what you mean when you say false, wrong in some sense, but it's really an undefinable. Here's the undefined terms. Well, in set theory, we replace the notion of true with the notion of in. You're in the set. I say out, but really we should say not in, right? That's the equivalent of false. A logical statement is going to correspond to a set. And if you have to need something that's got the sort of status that a sentence did in logic, that's remember what a sentence was. It was syntactically correct, but you couldn't assign it a truth value. You couldn't say, yes, this is true, or no, that's false. Well, a collection is sort of the same thing in the set theory world. We say collection to mean a set where we're not entirely certain what's in it, which is kind of a funny situation, but it turns out to be useful to make that distinction. Well, and by contrast, think about what that says for a set. That's a collection where you know for sure what's in it. You show me some element, and I can say, yeah, that's in, or no, that's not in, with absolute certainty. That's what makes it a set. So I've said that much about sets. Let's see this correspondence up close. We'll talk about sets and their corresponding objects in logic. If you have a statement P of X, that's going to correspond to a set. And it's the set that consists of the elements of our universe that make P of X true. That's a nice way to make the correspondence. So P of X being true for X means X is in the set S. You call that the truth set. So S is called the truth set of P of X. And if you need to refer to P of X in terms of S, you call it the membership criterion for S. Okay, so as an example, suppose the universe is natural numbers and P of X is the sentence X is even. Well, then the set is 0, 2, 4, 6, ... So you could say the membership criterion for being in set S is the logical statement X is even. Or you could say the truth set of X is even is S equals 0, 2, 4, 6. Those they're just terminology that go the two directions between the logic and the set. In the giant book, there's a subscript notation that's used to indicate these relationships, which is not a universal thing. This is strictly a foible in the book, but it does make sense at first to kind of keep track of what's a truth set. There's the set related to what sentence. You get that straightened out with the subscripts. So let's see, if you start off by having some set A given, we call the membership criterion M sub A. It's got to be an open sentence, so it's M sub A of X. If it goes the other way, that you're starting with a logical sentence, a statement, if that's what's given first, then you call the truth set of that sentence S sub P. So the set that corresponds to P. I guess that makes sense. All right, so a couple of just, getting the zen of sets, as it were. You need to be able to think about sets, well, accurately and with definitions, but also intuitively. Get your brain wrapped around what's in them, what they are. So the first thing is sets are unordered. If you think about having a bag or a box or something and you're just chucking things in there, that's the right idea. If you're putting things in order in like files in a filing cabinet, that's not a set. There's no order implied in a set. So in the book, they give the example frog pop over A. I think that's a reference to a Muppet movie at one time. Anyway, list those same words in some different order. That's just the same. They're the same set. So that's one thing. Remember that membership is a logical statement. This membership criterion is supposed to be a logical statement, so you know for anything in your universe of discourse, it's either true or false, one or the other. And that means every particular element of the universe is either in the set or it's not in the set. No gray area. Another thing to think about is membership is binary, right? It's either yes, you're in, or no, you're not. Um, if you need to have the idea of not only in the set, but in there a couple of times, like you have copies of an element, you have to do something else. But for regular sets, there's one copy or there's none if it's not in the set. So if you look at a data structure for capturing this in a computer, it would be a sorted list with duplicates removed. There's an example on page 168 that we should look at. So here's the example. Set 1 here has all those weird symbols, and set 2 has all these weird symbols. And for instance, the spades kind of stand out for me. I see they both have a spade. Well, there's another card suit, a diamond, that's in both of them. I see a capital A there. There's a capital A here. But this is horrible. Am I going to go through one at a time, finding the elements in, maybe go down S1, locate the elements that I see in S1 over here in S2, and then I'd need to make sure that S2 didn't have anything extra in it. Actually, you can probably tell they're the same length as lists. So, but look what happens when you sort them. If you see those same collections sorted, then you go, well, they both got a 1, they both got an A, they both got a diamond, they both got an E, an epsilon, a. Oh, that one's got an H and this one doesn't, so they are different. And that's the beauty of a sorted list. You can tell things are equal or not equal. Two sets are equal or not equal when they have exactly the same elements. These guys are not, because the top one has an H and the bottom one doesn't. You could keep going because I noticed they were the same size. Oh yeah, look, this one's got an S that's not up in here. Between pi and spade, there's an S, and not between pi and spade here. Okay, so sorted lists are the right thing to capture what a set is. Now, I just want to point out something about why sorted makes sense. These sets are supposed to be unordered. We don't care. You should think about the objects have been thrown into some container that doesn't preserve their order. But when things are unordered, it means you're free to rearrange them however you like, right? So in particular, you can put them in the standard order, whatever the standard order is. You can sort them however you choose. So when you see a collection of things that are pre-sorted, that are always going in increasing alphabetical order or numeric order, that actually tells you that that collection of things is an unordered set, really. So if everybody appears ordered, it means that somebody put them in that order, and that order really isn't important. I like to think about phone numbers for this. If the last 4 digits of your phone number are 8642, you can't punch them in as 2468. You've got to preserve that order. So, yeah. Some things order matters, in which case you'll see the digits or whatever the elements are in various orders, and sometimes order doesn't matter, in which case you're usually going to see the things in one of these collections in the same order, for instance, increasing. All right, so we'll take a little foray next into multisets. What are they? This is where this is the structure that lets you say, yeah, we can have copies of an element, not just it's not either in or out, but in there, and maybe I've got 5 of them. So what you do is for each element in a multiset, you write a repetition number next to it. I should probably have made an example of that, but I didn't, so I'll just quickly write one. If I have the set that's got 2 letter A's and 3 letter B's and an infinite number of letter C's. Oops, it would look something like that. You just have a digit or a number multiplying the entry, and you can make the thing infinity if you want. That means unlimited supply of those things. So In the text, they mentioned the Mississippi puzzle, which we'll spend a little bit of time thinking about. The Mississippi puzzle is this: how many different ways can you write those letters in order? I mean, how many different arrangements of the letters in the word Mississippi are possible? I don't want to do Mississippi right off the bat because it's too hard. So I have, oh, let's see, do this. That is some Scrabble tiles with a word from biology, genetics, actually called allele, pronounced allele. I found out just today how it's supposed to be pronounced because it turns out I've been saying it wrong all my life. This is, when you get a gene from both parents, you get a mix. Like if your mom has got blue eyes and your dad has brown eyes, you get the blue gene and the brown gene, and the brown gene is usually dominates the blue, so you end up with brown eyes. That's what an allele is. It's a variant of a gene, usually getting one from each parent. Well, that doesn't even matter. The reason allele is here is it's like Mississippi in the sense that it's got multiple copies of some letters. There's actually only 3 letters there, right? A, L, and E. But there's 3 L's, there's 2 E's, and there's only 1 A. So I want you to consider how many different ways I could lay those 6 tiles down on my, if I took the Scrabble rack and actually set the tiles on there. I wouldn't want to do that because then you'd be looking at them from above instead of square like this. But if I thought about how many different ways could I rearrange those letters, there's a clear answer that's not quite what we're after. See, there's 6 tiles, so I have 6 choices for what goes first, and then I have picked one and I've put it down, right? So then I have 5 choices for what comes after that. Then 4, then 3, then 2, then 1. And in a situation like that, you just multiply the numbers. So it's actually the factorial. 6 times 5 times 4 times 3 times 2 times 1. There's 6 factorial ways to order those tiles. But here's the problem. If I had these L's switched like that, is it any different? It seems like it's still the same word. So an arrangement of the tiles actually could correspond to, many arrangements of the tiles could correspond to the same arrangements of the symbols. So I've got 6 factorial things. I need to think about how many times they're overcounted by this idea of being able to switch things around and not really change it. The easy one to spot is switching the 2 E's, I suppose. I'll either have the E's in their correct order, maybe I could put a little mark on one tile or something, but I'll either have them in their correct order or not, or they'll be flipped. So the 2 E's are causing a double count of the arrangements, of the permutations of these letters. The 3 L's, however, how many different ways can you rearrange 3 things? Well, it turns out to be better to not look at 3 identical things while we're doing that, but let's look at 3 things that are different. A, L, and E, those are all different. How many different arrangements of those 3 things can we make? Since they're all different, this is the same as the Mississippi puzzle, isn't it? So yeah, I was trying to get at how many different ways can we arrange 3 things, and I've got 3 distinguishable things here. Well, I could keep the A where it was and switch those 2. Oh, and then here's one way to say it. There's 3 things. I got 3 choices for what goes first. Then there's 2 things remaining, and I got 2 choices for what goes next. And then there's really no choice, but let's call it 1 choice. I've got to put the E next. So there's 2 that begin with an A, then there's 2 that begin with an E, and finally there's 2 that begin with an L. That was 2 times 3, 6 things. So in our original word, allele, there are 6 factorial ways to, I can't spell this anymore, double L, E-L-E, yeah, there we go. There are 6 factorial ways to arrange the tiles, and that double counts the actual sequences of letters we see by 2 because of the E's and by 6 because of the L's. So we've got a total double count of 12. It's really not a double count if it's a factor of 12, but multi-count, perhaps I should say. So let's get that. It's 6 factorial under math, and under the probability menu there is number 4. There's the factorial side. 720 divided by 12. You get 60. Now, if you want to do the Mississippi puzzle straight up, you have to figure out what the multiset of letters is. What I'm seeing over there is 1M, right? I is the next letter. How many I's are there? Looks like 4 of them. And then S is the next letter. I believe we've also got 4 of those. And finally, there are 2 P's. The total number of letters is 5, 9, 11. 11 letters in Mississippi. Gee, I feel silly. I should have counted before we got started. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, we have 11 letters there. So if you think about the all 11 of those Scrabble tiles laid out, there are 11 factorial ways to arrange them, right? But this is there's many of them that would be indistinguishable based on, for instance, the permutation of the 2 P's. So we have to divide out by how many different ways could I order it based on the P's. Well, that's 2, or actually it's the same thing to write 2 factorial. I'm going to write 2 factorial because the rest of them will need those exclamation points. There's arrangements of tiles that will give exactly the same word, as it were, because they're just having the S's rearranged. So the overcount there is a factor of 24, or 4 factorial. There's another 4 factorial for the I's. And you can even include a 1 factorial for the M. So this is a thing called a multinomial coefficient, which we'll see again later. But it's sort of an interesting variant, or it's actually the binomial coefficients are a type of this. Notice how there's an 11 factorial in the top, and these numbers that are in the bottom, pre-factorializing them anyway, they add up to 11. So the reason they add up to 11 is that's how many tiles we had. And you're just counting the thing either by adding up to your repetition numbers or saying, no, there were 11 things total. So, well, we don't need to discuss that much more, but what is this as a actual number? So we want 11 factorial. And we need to divide by, I actually know these small factorials, like 4 factorial is 24. So there I just took care of the I's. Now divide by another 24 for the S's, and divide by a 2 for the P's. That should be the right number, 34,650. Still a lot, but a lot smaller than the 11 factorial, which was almost 40 million. Right. All right, so that's the Mississippi puzzle. Empire numbers come up again. We had those in our last activity, didn't we, in the last section? No, it was the one previous to this. But here's how you can actually succinctly say the definition of a vampire number now that we've got this terminology about multisets. A vampire number is a 2n-digit number v that factors as v equals xy, where x and y are n-digit numbers, and the multiset of the digits of v is the union of the multiset of the digits in x and the multiset of the digits in y. That allows you to have multiple copies of each digit that's in the fangs or in the digit or in the number. And for two multisets to be equal, I hope this is clear, you have to have the same members, but you also have to set the same repetition numbers. Okay, power sets is another interesting construction with sets that comes up in this chapter. So, given some universe, you can create subsets of it by selecting some number of use elements. Right? If you pick out a single element, that is known as a singleton set. And let's suppose the universe was something simple, like that was the worst curly brace of all time. It's made it even worse. Curly brace, there we go. Suppose we got 1, 2, and 3 as our universe. Then here's a singleton set. 1. It's just a single number, but we put set braces around it. So think about that as you're not just holding on to a number 1, you've put it in a gift bag, and you're holding a bag that's got a number 1 in it. You could have, here's a way to refer to the sets that have a particular size. You just use a little hyphen notation. So a 2-element set could be called a 2 set. What about no elements? Is that okay? Can you pick no elements from the universe and put them in a set? Yeah, it looks like this. You write down 2 French braces with nothing in them. That's the empty set. Notice I want to point out there's a reason this is in bold here. The empty set, but a singleton set or a 2 set. Why is the used with empty set? There's just one. It's a unique thing. There is just one empty set, whereas there are usually multiple singleton sets, and many, and more 2 sets, etc. Okay, so what's the power set? It's the set of all of its subsets. Now, we might be able to do that for an example like 1, 2, 3 here. I've got 2 of them. Do you know how many there are total? One way to think about it is this. If you're trying to build a set, think about doing it at random. Flip a coin for each one of the members of this universe. So flip a coin for 1. If it comes up heads, you'll put 1 in the collection, in the new set you're building. If you flip a coin for 2 and it comes up tails, then maybe tails means it doesn't go in. So heads, tails would mean 1, 2, but not 3 are in the set. So how many outcomes are there for 3 coin flips? It's like binary triples. There are 8 such things. So there's only 8 elements to come up with. I could do that by hand. I'm choosing not to because I want to show you some stuff with Sage, but we'll do that on the computer. So that brings us to the next section, computing. Before we jump over to CodeCalc, I just wanted to say a little bit about it. We're going to look at power sets in there. We're going to look a little bit generally about how you can use the system to model sets. Yeah, there are a few other things we'll look at, like the cardinality of a set, which is just a fancy way of saying how many things are in there. What's its count? Unions and intersections, those are other things you can do with Sage. On the programming side of things, this gives us a chance to talk about a Python concept called an iterator. It's not just Python, many languages have this. But it's very useful in programming, so we'll give you a few examples of that. And then we'll be wrapping up. So let me pull up the CodeCalc window. I actually pre-typed things because I think it's sort of a waste of our time for you to sit here watching me type. So first thing I've done here is a line where we've got 2 different ways to define a set. The first one is A with curly braces around the elements 1, 2, 3, 4. And then, by the way, this is a very common idiom in Sage to define something, then write a semicolon, and then name that thing. The definition of the set A doesn't produce any output. So when I write A by itself, the semicolon basically is just used to separate things that should be on different lines, be able to write them on a single line. But when you write A by itself, it echoes what's the value of A. And here, the second thing here, B is set equal to, there's a command, a function, set with a capital S, that takes a list, 1, 2, 3, 4, and then we have it echo B's value. And I'll execute this, but you can see the output that it produces right below it. we've got to go off and find ourselves a server to run this on. There it is. Now, those don't look the same, do they? Yet, you'll notice that the next line, A is equal to B, comes out true. So this highlights something that's a little confusing inside of Sage. There are actually two kinds of sets, Sage sets and Python sets. The first thing I've done here, I hope I'm getting this right, I believe the first thing is the Python usage for a set. The second thing is a Sage set, and there's a slight difference in them, but they do know how to correspond with one another. So if you ask, if you've got a set that's defined in the Python way and a set that's defined in the Sage way, it will say they're equal if they're equal. Okay, so what I wanted to do next was show you that you can have sets inside of sets. That is, you can have a set as an element of a set. So I'll admit the first time I typed this, I did not have that first line in there. Let me comment it out and you'll see what happens. If you just said B equals 1, 2, and the set that's got A and B in it, and type what B is, it does this to you. And I find the error messages in Sage a little difficult sometimes, but usually scan right to the end of them and you'll find the meat of the issue. It says name A is not defined. I think we talked about this the very first time I opened up Sage, that computers are dumb. It doesn't know that you're just creating a new letter that you want to use. So if you want it to understand that A is just a variable, you have to tell it so. There's only one variable that's built in, and that's the X. Other than that, you have to say. And the way you do that is the var command, which takes as an argument a string that tells it how to express the things on the line. So that means that if somebody types A on a line and hits Shift Enter, it's going to come back with an A. These could have been done as separate things, but it does have a syntax where it understands if the string has a comma in it, it'll assign the A to the A and the B to the B. So now that that's in there, that definition of A, we can run this, and we get a set that's got 1, 2 in it, and the set BA in it. Now, this is particularly bad because I've got a Python set that contains a Sage set as an element. I probably should have done this differently. Let's just check how this looks if we turn this guy into a list and apply the set operation to that list. Now I've got a Sage set that's got a Sage set inside of it. Woohoo! Okay, so when you have an object like B there's always a good idea to check out the member functions of it. It happens, everything in Sage and everything in Python is of a certain type. It's known as a strongly typed language. So B is of type set, and there are certain functions that are defined that are applicable when you're dealing with sets. If you put type B and a dot and then hit tab, you'll get a list of those functions that are applicable towards sets. Many of them are kind of hard to deal with, but here's one that's nice. Cardinality. Now that's a function, so we need to add some braces or parentheses after it. It says the cardinality of B is 3. Well, but look at it. It's got 4 things, doesn't it? Cardinality is supposed to be the size of the thing. And this is actually the right number, 3, but I think this is somewhat confusing to people at first. The reason this is 3 is what it's got in it is 1 and 2 and a box. And you don't look any further at the contents of that box. You just say, I've got 1, 2, and a container. That's the 3 things that are in set B. The container happens to have 2 more things in it, but that's a deeper level of recurrence, I suppose. The other functions you can do, there's one called a union. Now, we had A was 1, 2, 3, 4, right? Let's go back a little bit. Yeah, A was 1, 2, 3, 4. B now has 1, 2, the set of A, B in it. So if I do this union, I should get, I've got mixed types again. Darn it. Well, that's okay. part of the point is for us to get facile with switching back and forth between set in the Python sense and set in the Sage sense. They're both the same thing as set in the mathematical sense, just a difference in implementation. You see, I think the main issue is that Python sets can't be infinite, whereas Sage sets can be. Well, anyway, another way, quicker way probably to get the cardinality of a set is to ask for len, because ultimately inside the computer, a set is a list. It's an ordered list with no repeats in it. So the length of that list is how many elements, in other words, the cardinality. And len is a lot less to type than cardinality. So. Okay, so we've got a next thing is another operator for a set. It's actually written not in the member function sense, but as a function that takes a set as an input. And that creates some object that it just describes here. It doesn't even tell us what it does, but that's an iterator. That's the programming construct that I wanted you to know about. Now, you've actually seen iterators already. The range operator that returns the numbers from 0 to n-1. That range operator is an iterator. It's a particularly simple one. Anything that has the concept of I can go from where I am now to the next thing, and sometimes you can program that really inexpensively. You can figure out how to go from where you are now to the next one without having to list all the things. So for instance, the range iterator, when it iterates through the numbers from 0 to 999, it doesn't first make the whole list of 0 to 999. It never needs to. It knows that if I'm at 412, the next thing is going to be 413. It knows how to move from one to the next. That's what an iterator is for. It's a way to encapsulate the idea of saying I can run through this whole list without having to create the whole list. So the object we just created there with the subsets of A is an iterator. So let's use it in here. For S in subsets of A, actually, I wanted to show you a little progression here. Let's first just print S. What the things that are returned by this iterator are not sets, which is I don't know, I think that's strange, but there must be a good reason for it. These are lists, square braces rather than curly braces, and it doesn't say set of anything. If you want them to be sets, you can create a set that's got the same contents as that list, and then print the set rather than the list. And that only has the effect of putting everybody in curly braces. So it's not a big deal, but it conceptually is sort of important. This is getting me the subsets in the power set, the sets in the power set of 1 through 4 in a funny order. So the next thing I've done in this worksheet is I wanted to see them in the what I consider the usual order, which is based on how big they are. The first thing is, you see how it is in there? The first thing is the empty set. And then there's 1, 2, 3, 4 singleton sets. And then there's a bunch of 2 sets and some more 3 sets. And finally, the entire set, 1 through 4. So this is code to make that happen. For I in range 5, for S in subsets A, that's creating the iterator, if the length of S is I, I'll print it. So first time through that, I'll only print the empty set. The next time through the outer loop, I'll print the 1 through 4 singleton sets. The next time through, I'll print the pairs. So yeah, I probably don't need to run this because it's already there in front of us. But that's it. That's it. Interesting point I should make about the numbers of each kind, of each size there. You notice how there's 1 empty set, and then there's 4 singleton sets? Well, of course there's 4 singleton sets. There's 4 things in the universe set. 1 through 4 is what we're working out of. So put any one of those things inside some curly braces and you've got a singleton set. How many pairs do we have? 1, 2, down to 3, 4 there. count those, there's 6 of them. And then there's 4 of them that have 3 members. The 3 set, there's 4 3 sets. So you can say that. Notice that's the same number as there were singleton sets. Now, this is sort of a standard thing you'll see. The 1-element sets are in what's known as 1-to-1 correspondence with the 3-element sets, or the n-1 element sets in general. It's like, well, the correspondence is which thing have we left out, right? 1, 2, 3 doesn't have 4 in it. 1, 2, 4, that doesn't have 3 in it. 1, 3, 4, that's missing 2. And 2, 3, 4, that's missing 1. So we have the same number of 3-element sets as we had 1-element sets, and we also have the same number of 4-element sets as we had 0-element sets. That is, the entire set 1 through 4 is considered a sub-collection. That's when you make the choice, yeah, put it in for everybody in our universe. Have you seen those numbers before? Probably. I know. That's one of the rows of Pascal's triangle, another place where that stuff turns up. And what does all that add up to? 16? I think I said to you before in this scenario where we have the subsets of 1, 2, 3 that there are 8 subsets. I didn't write them all down. We could get Sage to do it in a second if you want, but there were 8 subsets there and 16 here. Are you getting a sense of why they call this thing the power set? So while we're here, I thought it would be fun to show you something that's related to one of the exercises in one of the activities we did about partition numbers. So there's a constructor for partitions, but what it does is something symbolic. That is, so I've said P equals partitions of 8 there, and if you execute that code, all it says is partitions of the integer 8. If you think that's creating an iterator, as I did, you're wrong. It says false, so it's okay. There's a way to create an iterator from it. I equals iter of P. Is I an iterator? Yes, it is. Okay, so then you can actually run through the elements of the partition and print them out. So that's what this little piece of code does here. And that's the partition where there's just one chunk and it's 8. This is 7 and 1. 7 plus 1 adds up to 8. 6 plus 2 adds up to 8. 6 plus 1 plus 1 adds up to 8. Notice that these are multisets, right? It's possible to have repeats of some of the elements in a partition. It was just something we did in the last worksheet. My memory's failing. Perhaps it was the one before that, was to look at the question of things having an odd part and things having distinct parts. That is, partitions having odd parts versus partitions having distinct parts. And there's this funny little theorem that says they're the same. That is, there's exactly the same number of partitions that have that consist of all odd parts as there are things that have all the parts distinct from one another. So what did I do in this code? I defined a function called hasOddParts, and it takes a list L, so I'm using L to remind me to list. What I'm going to do there is run through the things in L and check out their value mod 2. If their value mod 2 is 0, then I found an even part. Right? So then I return false. And if I make it through this entire array, the entire list L, without ever returning, then I know I didn't find any even things, so I return true. Does it make sense? So how about this other function? This is pretty quick too. A little bit, a little harder to understand, I suppose. We're defining a function called hasDistinctParts. Again, it takes L as its input. I define a set that is empty to begin with. And then for each member of that list, which is the list of numbers in the partition, I do a check. If J is already in the list, J is already in the set S, that means we've just found a duplicate, right? We found something that's not distinct. So we'll return false. If we make it through this entire loop and never did return false, well, then we'll return true. But if I didn't have this line in here, it all wouldn't work. What I'm doing there is adding this new element J into the set S so that, we don't always just have an empty set here. The first time through the loop, wherever the first thing in L was will now be in the set S. And so from there on, we'll be comparing things against whether they're equal to, whether they're equal to whatever that J was. Yeah, so here's a little, what's the word? Demonstration that, again, the set of things that have odd parts and the set of partitions that have distinct parts are the same size. So first I set up two empty lists, one O for odd and one D for distinct. And I'm just going to run through X in the iterator for that partitions. We'll print the thing just so we know where we are in it. And if the has odd parts function returns true for that guy, we'll append it to O. This is another set theoretic, or actually in this case, list theoretic function. That's a member function of any list has the ability to append to itself. And if it has distinct parts, we'll append it to D. And then when we're done, we can see what's the size of O and size of D. Ready? Well, this will be super fast. Whoops. What did I do wrong? I never reran these. Got to define that function before you can use it. Okay, now we can do this part. Yeah, that was quick, right? That's partly because it's a small example, and partly it's because of the power of using an iterator. That went through all the partitions. How many things are in O? 6 things. How many things are in D? 6 things. And there's no reason we couldn't get a little bit tougher on this. Let me change the code right here. For I in iter of the partitions of, how about 12? That'll be a pretty big number, right? It still went pretty quick, didn't it? 12, 11 and 1, 10 and 2, right on down until you get 12 ones in a row. How many of those partitions have odd parts? 15 of them. How many of them have distinct parts? Also 15 of them. If you want, you can actually look at the things, but there's probably too many of them for us to do much but look at them and go, yeah, there's a bunch of things there. One thing that's sort of interesting to notice is that these have the same number of things, but mostly they're not equal, but they can be. So it's the correspondence is pretty weird. Notice how there's an 11 and a 1 there, and there's an 11 and a 1 here. This one's got a 10 and a 2, but there's not going to be a 10 and a 2 in here because 2 is even, so is 10. Nothing in here is going to start with a 10 because these are the odd ones that are at the bottom of the page. Okay, one last bit of Sage coding I thought would be fun for you to do, which is to iterate the subsets function. And I'm going hog wild on it. I'm iterating subsets of subset of subset of subsets. So what does that do? Maybe I should be a little kinder and first say, here, let's just comment that out for a second. What are we going to have if P there was just equal to the subsets of an empty collection? I don't know why I wrote it that way. I feel like I should have written it as set with an empty list in it. Huh. So the subsets of set with an empty list in it is this one thing. Now, if we write that as a set, it's interesting because you should really write curly braces around the element. So it's actually a pair of braces around another pair of braces with nothing inside them. Philosophically, that's kind of fun. It's like a box that has a box in it, and the box inside the box is empty. But the outer set is not empty. It's got a box in it, right? Funny. What if I threw one more iteration of this? Subsets of set S. I need an extra paren at the end, don't I? Oops. I spelled it wrong. I didn't get an S on that. Another place where the Sage error message is very confusing, but you get down to the end and it tells you subset is not defined. At first my brain went, yes it is, but it does have an S on the end. So now the subsets of the subsets, the power set of the power set, by the way, you can type power set as well, but it's more typing, so I don't. That has two things in it, and the two things are a little bit bizarre. One of them is an empty box, and the other is a box that's got an empty box in it. Let's go to the one I started with. Subsets, so this is the power set operation applied 4 times to an empty list. It's got a lot of stuff in it. If you count this up, there's 16 things here. Each thing on the line is an element of a set, so there really should be kind of curly braces around the whole of these. One up high at the beginning, one down low at the end, and then there should be commas after every one of these. But it's just printing them out on a line, so we're printing them element by element rather than as a set. Wow, what are we looking at here? There's some real funny business. I'm trying to see some of the more interesting ones, like that right there is a set which contains 2 things, an empty box and a box with an empty box in it. Or, let's see. Well, this whole line is kind of intriguing. This is a box that has in it a box that has an empty box in it, and another box that's got an empty box with an empty box in it. That is nested 3 deep. Okay, so I think that's enough silly business with Sage. Let's run back to our slides. I thought we talked about that. Okay, wrap up. So just a couple of pieces of advice. This stuff about empty boxes actually comes from my childhood. We had a sister that was a little gullible, and we would sometimes, for Christmas, give her a present that had a big box, and inside the big box there was a smaller box, and inside the smaller box there was often yet a smaller box. And by the time she got done, there was, 5 boxes may have been unwrapped, and there was nothing. It was cruel, but we did it anyway. You can use this notation as sort of a. It's not the letter phi. It's actually a separate symbol for empty set, but it looks an awful lot like it. It's more of a 0 with a slash through it. Or you can use a pair of empty braces for the empty set. But you cannot do this. You can't write set with the empty set symbol in it. And for some reason, there's a temptation. People tend to do that. But that's wrong. This is like the pranking your sister moment. This is where you've got an empty box inside another box. These are both empty boxes. This one, by definition, is just the symbol for an empty thing, and this one is writing it out, braces with nothing in it. I already said that. That's a very different level of prankery from merely giving an empty box. I agree with that. This is you have to be quite cautious about the way you use these French braces around things. Last thing to notice, if I have the element X and the singleton set with the element X in it, those are distinct. You can tell the difference between, a container that's got an X inside and a plain X. It's like if there's a Christmas present as a puppy, and there's a box with a puppy in it, that's very different from just a puppy without a box around it. So next time we'll be doing 4.2. It'd be great if you read that a little bit beforehand, and have a great rest of your day.